Hello, Andrew. We are about to begin this live stream. So,
hello, everyone. We are going to begin our next presentation from Velo3D and the Barnes Group advisors on the topic of how to fast-track certification and qualification for metal additive manufacturing. I would like to introduce Dr. Zach Murphree, Velo3D's VP of Technical Partnerships. In previous roles with Velo3D, Zach served as the Director of Business Development, Head of Product and Applications, and Head of Hardware Engineering. His background includes engineering roles for energy companies, where he was in charge of introducing metal additive manufacturing technology to Fortune 500 energy company. Prior to Velo3D, Zach led North America sales for Concept Laser. And I would also like to introduce Dr. Slattery. He was most recently the Chief Scientist for Additive Manufacturing in Boeing Research and Technology. He is responsible for developing and integrating the technical roadmaps and development plans for Metallics AM for the entire company. Prior to that, he was the Chief Scientist for Metals, Ceramics, and Mechanical Systems in Boeing Research and Technology. He served as the Division Chief Engineer for USN and USAF fighters and US Army rotorcraft in Boeing's military sustainment organization, including international operations. He was the technical and programmatic lead in implementing the first in aerospace metal additive manufactured structural aircraft components for both spare and production parts, along with 5 other industry first technology implementations. Kevin currently holds 34 US patents with another 15 applications pending. All right. And I don't see Kevin here. Kevin, are you here? Are you able to turn on your microphone and camera? Let's see.
he says they're on.
I'm not seeing Kevin's screen. Is anyone else seeing it?
I can only see my screen.
Me as well.
I'm coordinating with him. He's going to do a hard refresh, but if you want to start the presentation, feel free to.
Okay.
I'd love to. I think Kevin's first in the presentation, so it may be best to wait for him to join.
All right. Kevin, if you hard refresh, it might re-add you. All right, I don't know if Kevin may still be having some technical difficulties. Zach, if you want to go ahead and get started on your portion of the presentation, that would be great while we're waiting.
Okay.
Thank you.
Yeah, absolutely. So Kevin and I were really wanted to present today on some of the Barnes Group advisors' background And I think one of the things that Kevin was looking to present was kind of their qualifications as a group and some of the background that they have as it relates to taking parts, metal additive manufactured parts, through the entire life cycle, from initial ideation through the actual printing of parts, and most importantly, through the qualification and certification routes.
That's right. And so, Zach, Kevin will be speaking through my mic. Kevin, feel free to continue. Yeah.
Okay. Good afternoon, everyone. Kevin Slattery here from the Barnes Group. So I'll just give you a brief intro to what we do. Our mission is really to accelerate the adoption and industrialization of additive manufacturing. We're the largest independent AM technical consultancy there is. So we're machine agnostic, process agnostic, and in fact, with some of our clients, they will say we're AM agnostic, whether or not to use AM or not. And that's how we help people, how to decide whether or not they want to start with AM, what their journey through AM will be them, and then later on, helping to get them all the way up through, producing products that are qualified and certified for their usage. We have over 130 years of combined experience in additive manufacturing, and we're technical engineering based primarily. So today we'll talk a little bit about certification and qualification. So if you can move to the next slide, Zach.
Yep.
So one thing.
I think we lost Janet and Kevin. Sorry about that. Oh, I hear Kevin now.
Okay. Many people have many different versions of certification and qualification in very highly regulated industries like aerospace and medical. There are certifying agencies, government agencies, and very detailed descriptions of what those are and what the requirements are. But at the other end, for someone just making a part to hold an e-reader, in a way, you're certifying the part as well. So we use a very simple definition for certification that's very industry independent. It really means that the component meets design intent and is fit for service in a system. So really, it's the chief engineer. In the case of a highly regulated industry, it would be the chief regulator. But it's saying, yes, this will work and the system will work with it. And on a highly regulated industry, that can take volumes and millions of dollars of testing. For a very simple use for yourself, it can be something as it's the right dimensions and it doesn't have any cracks in it. And so coming up with your certification approach, if you're not in a highly regulated industry, is very important, and it ties in with design intent. Secondly is qualification. And qualification really just means that the part meets the design intent. And qualification has many different aspects that I'll cover at the very end about supplier, machine, and the process and the component. So the important thing to note there is that that you can consistently make hardware that meets that design intent. If you go to the next slide, please, Zach.
Yep.
Yes. to talk about. So we have, sort of 5 pillars for certification. And these are really based on what Dr. Jack Lincoln at the Air Force put out during all of his pioneering work on aircraft structural integrity back in the late 60s, early 70s, and all through the 80s. So the first of these is requirements and design criteria, which means you know what the component, what it needs to do, how long it needs to survive in service, and what happens if the part fails. The second is stability, robustness, and repeatability. So if you're making components or parts, if you don't have a stable, robust, and repeatable process, and that can cover robustness as both in terms of sensitivity to variables you can change and sensitivity to variables you cannot change. If your process doesn't meet those requirements, it's going to be very limited in what you can use it for, because it really comes up to the next items. Producibility. Can you make a part? Can you make the part you want by the process? Some processes are very good for making small parts. Some processes are very good for making large parts with different complexities. If you exceed those producibility limits, it's very hard to make a component that meets requirements. Finally, there's characterized mechanical and physical properties. So you need to know what these properties are. In the end, a designer and a stress analyst is going to design that part. They're going to analyze it, and they're going to have to say it has the strength or it has the thermal conductivity needed, or both, to meet requirements. If they don't have a number to put in their calculations, then they can't really do that. And so those properties have to be characterized. And then finally, you have to have predictability of performance. It's one thing to have good average properties or have known average properties, but depending on the application you're using, more or less, you have to be confident that you're going to get those properties consistently. A process with a 10 KSI average and a 5 KSI standard deviation, at some point you have parts with no strength at all. So you have to have that sort of predictability. And not only is that mechanical properties that are relatively easy to measure, but it comes into things such as types of discontinuities and their impact. And it extends very far into other properties beyond static, depending on the application, fatigue and such. A really good example of this is MMPDS that's used in aerospace that characterizes those properties with statistical significance, of which I don't believe any AM processes are currently in that. So in terms of the pillars, so what Zach's going to cover now are how the Velo 3D system actually supports 4 of those 5 pillars. Can't do much about you knowing your design requirements and such, but can help you with the other 4. And now Zach.
Thanks, Kevin. So Velo 3D maybe unknowingly set out to address a lot of the issues that you have with qualification and certification. And I've kind of rearranged the 5 columns or the 4 columns that we're covering based on the story of Velo 3D and really how we came to have the products that we currently have in the market. And I think when you look at the 4 pillars that Velo 3D does address, the first one that we really set out to tackle was producibility. And this is really kind of the core of our story is developing a process that allows the end user to make a wider range of parts. And so the point here was really to take the limits of laser powder bed fusion specifically, which is what our machine does, and expand them. And one of the main challenges with laser powder bed fusion is that there's this well-known 45-degree rule, which is essentially that any surface that is less than 45 degrees from horizontal will require support structure to be able to build successfully. So as a company, what we set out to do was to broaden that envelope. And over the last 6 years, we've been very successful in doing this. And you can see here some of the examples of the parts that weren't producible without a significant amount of support structure, but that are now within the realm of possibility of metal additive manufacturing. The first one on the left-hand side is shrouded impeller, which is a part that has always seemed like it should be a really good candidate for metal additive manufacturing, but in other systems would require to essentially fill the inside of the part with supports, which makes it uneconomical because removing those supports is very challenging. On the Velo Sapphire system, we're now able to print these parts down to fully horizontal overhangs on the shroud and to print them with very good mechanical properties. So they're fully dense and they have a good surface finish on the bottom of that shroud surface. This low angle capability also lends itself to inner diameters. So if you have manifolds or tubes that have larger inner diameters, we can push this up. Now we're at about 100 millimeter inner diameter. This slide says 40 millimeters, but we can actually go quite a bit bigger at this point. And then we're also able to print some very high aspect ratio, very thin features. And this is because of the architecture of our recoder system. So we can get up to a full 16-inch tall, 10 thousandths of an inch thick wall and print that successfully without having the recoder crash into the part. So being able to expand the producibility of the parts is a really big issue. And we think that we've done a good job to really address the breadth of parts that can be printed with laser powder bed fusion. While we were developing this process, we ended up building a machine that has what we believe is the most comprehensive suite of metrology and sensors of any laser powder bed system. And we did this not because we wanted to make all of this data available at the outset, but because we needed to understand what the process was doing and to be able to control it within a very tight window to print successfully. So we were setting out to have stability, robustness, and repeatability for us from a process development perspective. But one of the things that we found to be true is that the tools that we built into the system became very valuable for end customers, and especially valuable when you're working as an end customer to certify a part. So one of the really critical aspects of operating a laser powder bed fusion system is understanding if the machine is calibrated before you print a part. And specifically, the optical system is one of the key aspects of printing good parts. I like to quote a NASA spec, and I know that quoting specs is probably one of the nerdiest things you can possibly do, but the NASA Marshall Space Flight Center spec, the 3717, which is covering the production of parts with laser powder bed fusion for human spaceflight, has a very specific requirement around optical system calibration. And they recommend that the system's calibrated every 90 days, which is very reasonable. Normally for an optical system calibration, a field service engineer will come in and take the system down and check all of the galvo performance, the laser performance, all of the lenses, make sure the spot size is consistent. But one of the tricky things about the NASA spec is it says that if the system's found to be out of calibration, then all of the parts printed in the preceding 90 days or since the last known good calibration are now non-conforming and could be scrapped. And so if you're a machine operator, that could be $250,000 worth of parts, which is a very expensive proposition. So we're able to use the metrology on the system to essentially have one-click calibration. And what you see here on the left is a tool health readout that you get with every print as part of our build report that shows that the system is fully calibrated and nominally in spec before you print a part. It's also important as a machine manufacturer to give customers insights into the machine itself and how it's running and how things are changing over time. So we've built Assure, which is our quality assurance and validation software, which we just found out today actually won the Edison Award for real-time metrology. It won the gold medal in the Edison Award, so we're pretty proud of that. But we've established control limits on all of the key metrics, and you can see these control limits plotted as a function of time for every system in your fleet and for all of the key parameters, and kind of go back and drill down in time and see how things are drifting or how things aren't drifting, and if anything needs to be addressed in order to keep the machine nominally operating in spec. And kind of along the same lines, the other aspect is making sure that builds are executed as they're supposed to be executed. And so with that, we have what we call our heat map, which is essentially a time log of all of the critical parameters. So oxygen level, humidity levels, the amount of powder in the system. peak height. So we're actually able to measure a 3D scan of the powder bed before and after lasing. And this is essentially like a structured light scan where you get data over the entire build plate in Z and with a resolution of about 15 microns. So we can track the peak height of parts as they're being printed layer by layer. The third column that Kevin mentioned was the characterized properties. So we've spent a pretty decent amount of time characterizing the properties and working with the Barnes Group advisors to align those properties with what's expected of laser powder bed systems. So one of the key data points that you'll see across machine manufacturers is the average mechanical properties and the minimum mechanical properties. And this is kind of the most basic set of characterization that you can get. One of the things that we're working on as a machine manufacturer, which I think customers should really be asking for, is a more in-depth statistical characterization of the properties. So we like to go into a little bit more detail where we have the averages of, for instance, here are static mechanical properties, as well as a mean minus 3 sigma. And this really gets back into the repeatability issue, which is that you need to have confidence intervals for the material that you're making in order to establish design allowables and to kind of take the same methodology as the MMPDS that Kevin was referencing. So as an example, this data set is across 9 unique builds, 6 different machines, all located at different sites. There's 2 laser paths per machine, so it's 12 independent laser paths performed over a 6-month period with 3 powder lots. And when you have that big of a group of data, then you start to develop more and more confidence in the mechanical properties and really start to have true confidence intervals around the mechanical properties. And then the last part of the predictability of performance is really what's kind of the core of Assure, of our quality validation product. So this is the predictability of performance. This is being able to tell whether a given part that you pull off the machine is good or not. And I think, to reference again the NASA spec 3717, one of the key takeaways there is that all laser powder bed systems, or the vast majority of laser powder bed systems, are capable of making very high quality parts. And I don't think there's any argument there. The real question is whether a specific part that you pull off of the machine is of high quality. And without some way of kind of tracking that during builds and across layers, it's very hard to know without some pretty significant costs associated with the non-destructive testing. So what we've done here is to establish a correlation between a multi-sensor measurement that we're taking and porosity. And so we actually have a very high correlation between the predicted porosity and the actual measured porosity. And this is a statistical measurement, so it's not necessarily sensing individual pores, but it is giving you a confidence interval around the quality of the material that you're making. So this is kind of a summary of the way that Velo is approaching the qualification and certification goals of our customers. And I think it's really important that the machine manufacturers recognize the needs of the customers and work to make it easier. And this is what's really required to be able to drive additive part adoption across some of the more highly regulated industries. And we're happy to be doing our part to help there. Kevin, back to you.
Thanks. Just a little bit as well on qualification. So there's many different types of qualification, and an overall OEM might have qualifying a process, which means we can use this process for parts in general. But qualification in general, once you get beyond that, generally you get a machine or a process qualified, you get a facility qualified, and a lot of the facility qualification has nothing to do with what process you're doing, or the AM machines, right? It's having a quality system in place. It's having controlling your material, things like that. The machine process is very much going to be around the process itself, and includes also things like having your firmware and your hardware and your software locked down and having a fixed process in place. And then finally, there's the part qualification. And the part qualification for very low requirements parts may be that we have some witness coupons that get tested and the part's qualified, and qualification looks the same as lot acceptance testing. At the other extreme, qualification can have multiple destructive tests involved, excising coupons, or actually even performing a component test, depending on how the actual subsystem is qualified or certified for the part. Once again, you have to figure out, it starts with your design requirements and criteria, and you work your way to figure out what your component qualification entails.
And I think with that, we're essentially done with the presentation. Happy to take any questions that you might have.
Can we just go off the list over there in the dialog box?
Sure. So I can help you with managing the Q&A if you'd like.
Okay.
So we have a question from Lucy asking, support structures are also used for heat dissipation. How do you work around this, or are you still stuck with this requirement?
No, I think it's still, so there are physics limitations, right, to basically being able to produce parts correctly and to produce high quality material. And I think one of the things that we tried to tackle as a company is that there is still the requirement to remove heat essentially from wherever you're melting. And one different approach that we've taken is, instead of having the support structure so that you are able to remove that heat, if you instead are very judiciously applying the heat, then you don't have so much heat that you need to deal with at the end of the day. So it's kind of a different mindset, where instead of applying a process that's kind of blind to the geometry, that doesn't really take into account all of the metal and the powder around where you're melting at any given time, we are applying a very specific process that is very well aware of what's around it. And that allows us to get away without needing the supports as a heat sink, essentially.
Awesome. Thank you, Zach.
Mm-hmm.
Another question from George. Has Velo3D or Velo3D users been successful in bypassing industry NTD or other test requirements with sensor data from the machine?
So it's something that we're working on currently. And I think one of the challenges there is that you need to have very good confidence in the sensor data that you're generating. And so there's a white paper on our website that was kind of the initial qualification of the Assure product with Stratasys Direct, who is one of our customers and has one of our systems. And we're working with them and with some of our other customers who are actually in full-scale series production, specifically of like rocket engine components, to make sure that the data that they're getting is sufficient to allow them to eliminate some of those secondary quality control measurements.
Thank you, Zach. A question for you, Kevin. When metal additive manufacturing is published in the MMPDS, will this mean we can move from 100% part inspection to part sampling inspection schemes?
Well, I'll give a little background there. The commercial and military aircraft fleets, when you look at airframes, probably have somewhere around 1 trillion component flight hours. So number of flight hours times the number of components made out of wrought titanium. This is outside of the engines. And probably the number of MT-related failures, material and process-related failures, versus aging and damage and corrosion, things like that, on titanium is probably can fit on one hand. Probably less than 5 of those in the history. Every wrought titanium part still gets 100% volumetric, usually an ultrasonic inspection, and 100% surface penetrant inspection, still to this day, with the exception of bent formed sheet metal. And those allowables have been around for decades. So I don't think in a highly regulated type area and a very mission critical type area like aerospace, you'll see that, getting rid of that. What I do see, and what is unique about AM, is I think the potential to get to doing an in situ type inspection, an independent inspection, every layer or every couple layers, followed by some final type of inspection, I'm very optimistic that that'll happen in the next 20 years. Whether or not that won't have anything to do with having MMPDS allowed as well.
Awesome. Thank you, Kevin. And I think we have time for maybe one more question. So the one with the highest votes asks, why do you use peak height as layer metric versus other surface profile characteristics?
So we use peak height as just kind of an indicator of the behavior of the parts within a layer. Assure actually provides the full map. We call it a height map.
You're muted. Janet, you're muted, so I can't hear you.
Can you hear me?
You're perfect. Yeah.
All right. So we provide the full, on a layer by layer basis, there's two height maps. There's one before lasing, or one before recoding, and one after recoding. And the before recoding gives you the behavior of all the parts, and it's a full array of data, right? So it's on a 100 micron by 100 micron pitch, you have data every 15 microns in Z. So it's quite a bit of data. And we do that twice per layer, before and after the recode. So we use peak height as basically an indicator that shows whether or not the parts are behaving, and it takes the highest point on any given layer and plots that as a time series. Because otherwise it'd be kind of an overwhelming amount of data to have to interpret quickly.
Awesome. Well, thank you so much, Kevin and Zach, for participating and joining us today. And thank you for being patient with the new technology we're using. We look forward to chatting with you later in the day as well.
All right. Thank you.
Thank you.
Thanks.